Uh, Thanks everyone for joining the session today. Let me start with the introduction. So I'm Sumit Mathur, Group Engineering Manager at Intuit. I manage the traffic team. And with me, I have Sushanth. He's a Senior Staff Engineer in Intuit. Yeah. So Intuit is a fintech company based out of US, and we have products in accounting and tax. We are on the mission of powering the prosperity around the world. And we believe in open source technologies, and some of the contribution to open source includes Argo, Numa, Admiral. And we are the consumer of the open source technologies, which includes Kubernetes, Istio, Prometheus, etc. Yeah, we are the part of a traffic platform teams, which provides the platform capabilities to rest of the Intuit developers. So our customers are the Intuit internal developers. They use our platform to develop the business logics and all the products that Intuit has. The main goal is basically to abstract the network platform from them so that they can really focus on the development of the product. And this is the scale at which we operate. We have more than 300 plus Kubernetes clusters with 16,000 namespaces. More than 10,000 developers are using these platforms with more than 2,000 services on these platforms. Yeah. Some of the contribution from the traffic team includes Admiral and Navic. We are going to talk about both of these in the later part of the session today. Yeah. This is our agenda. We are going through touch base some of the basics of traffic, and then how does the Intuit traffic platform looks like, and our journey while building this platform in the last 10 years, which includes like the different capabilities that we have built in this platform, including authorization, rate limiting, and config distributions. Yeah. So let's start with a 2 minutes intro, like what is an API gateway. So let's consider a developer in your company who is developing the APIs, and once the APIs are ready, they get their first client who started using it, they share the credentials, and the things really works well. But as the business grows, right, you get multiple sets of clients, like desktop clients, mobile clients, the browser clients, or you may have a services within your own enterprise boundary which want to consume these APIs. Or you may have a third-party apps which want to leverage your APIs to build the products, right? So now the focus of the developer who was developing the business logic APIs will change to how do I protect my APIs, right? How do I authorize, like who can access what? And at the same time, how do I make sure like one client does not consume all the capacity of my services, right? So that's where API gateway comes in picture. All these services interact with the API gateway. API gateway is the front door. Once it goes through the API gateway, then it makes a call to the backend services. So this is at high level what's an API gateway. Now let's see what is service mesh. So consider a architecture where a service is deployed in a Kubernetes cluster. So consider like service S1, which is deployed in a Kubernetes clusters in a multi-cluster scenarios where it is communicating to service 2 and service 3. Now, to get a similar capability like API gateway, what you need is something like this, right? Where service is communicating to another service through an API gateway. In our case, in Intuit, this API gateway is again deployed in the Kubernetes clusters, hosted in its own VPC. So that means every time the request need to go to a different networking zone, and that incur the latency, and at the same time, like it's not a really cost-effective way, right? So what we really want is each of these services, because we are in a Kubernetes where we have a concepts of containers and all that, what we want is a mini gateway which is running alongside of your own service, right? So in Kubernetes, we have a project called Istio, which really provides us the service mesh kind of capability. It helps us in service management, traffic management, right? So that's where Istio comes in picture. So now, knowing like what is gateway, what is service mesh, let's look into the Intuit traffic platform, what we have done basically. So Intuit traffic platform basically includes, like it combines both API gateway and service mesh together, and we call it as a traffic platform. So all the browser traffic or the internet traffic comes through a gateway, and we call it as a north-south traffic. And anything within the Intuit enterprise boundary, it goes through a service-to-service communication through a service mesh, right? So this is at a high-level network diagram. Some of the features of this platform is like front door for all the services, all the requests, and service-to-service communication. Other things are routing. So we provide both static and dynamic routing, security, authentication, authorization, metrics. So it's a source of golden signal metrics for all the Intuit services, access logs, rate limiting, and traffic dialing. So some of these are the core capabilities that we have built within these traffic platform, and that's what we are going to talk about. And this is the stats. Like on a daily basis, we get close to 30 billion requests, 1.5 million transactions per second. The availability is 5 nines. Golden signal I just talked about, and then it's a very performant platform with P99 is less than 30 milliseconds, and self-service. Yeah. So I think the entire traffic platform is built on the principle to provide a self-service capability. So that means the users really don't need to understand the integrity of the platform. We provide them the self-service, which is more an app-centric way. Users should come and do the app-centric way, and then we take care of translating those to the platform capabilities. And this accelerates the velocity. Now, let's go through the architecture. So some of the design principles while building this platform in last 10 years are like partitioning. So we want to make sure like partitioning is the first-class citizen for us. So the entire platform is sharded with multiple swim lanes. And these swim lanes are designed on the basis of the products that we have, like the business units, or on the security, like some are PCI compliant swim lanes, or on the basis of timeouts. Some services require a high timeout, or some services require a high payload, right? So that's where the entire platform is sharded across multiple swim lanes. It's a stateless and horizontally scalable. It's highly reliable. So the entire platform is resilient to entire region as well as one AZ failure. So we can still serve the same 30 billion requests with entire one region down and one AZ failure. It's highly cacheable, so and that's the reason it scale out very fast. We don't, at a runtime, depend on any database. Self-service, I just talked about it. Yeah. So this is the first design when we started our journey. So Intuit API Gateway is a multi-tenant API gateway. What does it mean, basically? So this is one of the deployment namespace where you have a pods. The API Gateway pods are running with its own load balancer. Let's consider a scenario. A service one is onboarded on API Gateway with its own domain name, service1.com. Now, what happens is whenever the request comes for service one, it goes to the load balancer, it goes to the pod, and it goes to the backend. It's straightforward, right? And if anyone do the NS lookup of service1.com, it get the IP of load balancer. Now, what is a multi-tenant here is, what we have done is multiple Intuit services are deployed on the same cluster using the same load balancer. So what does it mean is, all these service 2, service 3, they maps to the same load balancer. The request comes to the load balancer, then it can go to any pod. And then the pod has a routing logic, right? It understands, OK, if this is the domain name, then I need to route the request to service 2 or service 3. So that's what we call as a multi-tenant architecture. And this really helped us in reducing the cost drastically. As I mentioned, Intuit has more than 2,000 services, right? So the number of domain names that we have across all the environment is more than 20,000 plus. So that means if I have to map a given domain name with a one load balancer, it's a huge cost, right? So with this architecture, we actually drastically reduced the cost by mapping multiple services to the same load balancer and having a good routing logic within the API gateway to send the traffic to the backend. Yeah. So this is one design. Second thing is multi-swim lane. So as I mentioned, Intuit API Gateway is multi-swim lane where we are hosting, like Intuit API Gateway is spread across the multiple clusters, and each clusters can host multiple swim lanes. And this really helped us in doing a chargeback model. So we really want our customers to be very cautious about when I say customers, it's Intuit internal developers who are using the platform, to be very careful in using this platform so they know like the cost that it is going to incur. And so this is another snapshot where a single clusters can have a multiple swim lane. And this is another thing like where the swim lanes are spread across the multiple clusters. Now, knowing the basics like the multi-tenant and the multi-swim lane concept, now let's go one level down to understand the entire ecosystem of the traffic. So the API gateway, as I mentioned, is spread across the multiple swim lanes. And similarly, the mesh, service mesh, is spread across all the Intuit Kubernetes clusters. And there are certain services in Intuit which are still not on service mesh. So what happens is, for those cases, When the request comes through a load balancer to API gateway, those requests get routed to the backend through a NAT gateway. If the services is on the service mesh, then it goes through transit gateway. Now, to run these clusters, like all these 300 Kubernetes clusters for the service mesh, we have a admin cluster, which basically hosts all the admin capabilities or all the admin capabilities that we need to run these clusters. So first capability is service mesh. My bad, it's service registry. So service registry stores all the configurations that API gateway needs to bootstrap. So whenever the API gateway bootstraps, it gets all the data from the service registry, and then it keep on running. And we are going to learn more about it in the later part of the session, like how it refreshes that configurations as well. Yeah. We have another config service which provides the data to install the Istio on all these 300 Kubernetes clusters. Then we have a component called Navic, which helps in distributing the service configuration. So let's understand more about it. So we all know, like in Istio, if I have to configure capabilities like traffic dialing, rate limiting, or timeouts, we need to understand how to configure the Istio custom objects, right? We have to write the virtual services or envoy filters, right? So now consider where you have more than 10,000 developers, and we need to ensure like all of them to understand the service mesh concepts, write those filters, and then deploy those filters either on the client or on the service sides, right? Depending on the capability that we are configuring. That's a huge developer productivity impact. So what we want is to abstract those configurations. So we have a developer portal. Users comes in the developer portal. They provide the configurations more in the app-centric manner, like timeout is this much or rate limiting is this much. And then Navic reads those configurations, generates all the Istio custom objects, and then distribute it across the clusters, either on the client or on the destination side, depending on the configurations. Yeah. Third is Admiral. This is another open source that we did. So this helps in the service discoverability in the multi-cluster scenario. So let's understand this. So consider like you have a service with multiple clients onboarded on it, right? Now, the service can be in a multiple clusters as well. So how does the client know, okay, where to send the request? So that's where Admiral comes. So Admiral generates all those virtual services which helps in routing, and it helps in discovery of those services. Both of these projects, like Admiral and Navic, as I mentioned earlier, are open source. You can read more about these in the GitHub. The similar architecture is replicated in the second region to provide a high availability to all the services that we have in Intuit. And the thing is now, because all the services are highly available, we really need to have some capability to fail over. So the services in the Intuit can be active-active or active-passive, depending on the service capability. And for that, we have provided a capability called DNS Manager. And it's a single point of contact for the services to fail over both front-end, that is at the API gateway level, as well as the service mesh level. And to know more about like how do we fail over the services at scale, do attend a talk in the same hall at 2:50 p.m. My team is going to present about the more deeper of DNS Manager, how we do the failover at a scale. Yeah. So now, understanding like the different components of the traffic, let's start our learnings, like what are the different learnings that we have while solving the problems of building this highly scalable architecture. And this is not the only way. I think there can be multiple ways. So we are going to talk about only the journey that we have gone through. So let's start our authorization journey, how we built an solution, and then how we externalize it to OPA. So authorization at a high level is protecting your APIs, right? So let's say a service can have multiple APIs. One is your admin API. Second can be the APIs which can be used by the other services. So what you really want is there should be some rules to protect the APIs who can access what, right? So that's simply authorization means. And in Intuit, we have a developer portal where users can come and write those rules. So this is how one of the rules looks like. Yeah. Let's start with the design one, like how we build this authorization without OPA. So Intuit API Gateway is built on Jetty container, which is a web server or container. So we have a request handler with its own thread pool. So whenever the request reaches an API gateway, request handler takes that request. One of the threads take that request, the request passes through different policies in the request path, like authentication, authorization, rate limiting, and whatnot. And then eventually, it goes to the backend. So on the last policy that we have is the outbound policy with its own thread pool called outbound thread pool. And we really don't wait for the request to come back. And whenever the response is available, another thread picks up. So this also helps us in attaining that multi-tenant architecture I talked about, right? Where you are just separating both inbound and outbound. So this was really working well for us. The only issue that we had at that time was the logic of the authorization, right? The rules are outside, but the logic is still within the gateway code, right? Within the JVM memory of the gateway. So what we did to solve that thing is we moved to OPA. So we took a decision, let's use OPA. And what we did is, along with the gateway container, we introduced another container called OPA container as a sidecar. Now, when the request comes at a Jetty container or the gateway container, we introduced another component called SDK. We created another SDK called Authy SDK using Jetty async with its own thread pool. So whenever the request reaches the Authy policy, it makes a call to Authy SDK, and then one of the thread picks up that request, makes a call to OPA. And whenever the response is available, another thread picks it up, and then the request flow continues. So this really worked well for us to achieve a high TPS, and things were really working well until a certain point, right? So let's look at what went wrong with us with this design. So if you really look at it, we have something called rate limiting here, which makes a call to remote cache. We are going to discuss more in detail later, like why we have that concept. So, but if you see the thread, whenever this remote cache becomes slow, a lot of threads start blocking there. So we have a thread blockage there. And if it's really slow, what happens is this Authy thread pool is starved. You don't have enough threads to make a call to OPA. And that impacted the entire request flow for us. So to solve this, what we did is we thought, OK, let's introduce another thread pool. So between rate limiting and remote cache, we introduced another thread pool to solve this problem. But what we found is we have more policies in the request chain, especially like dynamic routing, which helps in resolving the outbound at a runtime. The request, again, we face a similar problem. So we thought, we looked back again our design, like what's going wrong here, and how we can solve this problem, rather than introducing these multiple thread pools. So when we really look at the data, what type of these requests are, we found, right, like many times, most of the requests are repetitive, right? So what we did is to solve this is, again, it's the same sidecar. But instead of using a async jetty, what we did is we used a sync jetty with a cache. So what it really helps us is, instead of making a call every time to sidecar, we can cache the response in the SDK, and we can serve it from there. So instead of introducing another thread pool, it's the same thread pool, and it gets the response from the SDK, and it really worked well for us. So we were able to achieve the same high TPS with a similar resource utilization. So yeah, let's look at the learnings from this. Introducing a async thread pool, it impacted the entire request flow at a high TPS, right? Now, if I have to solve this problem, I have to make intermediate steps also async, right? So that means all the steps need to be async. Now, this introduces another problem is, if I have to make this, then fine-tuning of this multiple thread pool is a tedious process, right? You have to keep on fine-tuning it, and what we observed is it often breaks. As you fine-tune, as your TPS scales, or you get a different sets of services, it often breaks. So these are our learnings with Authy when we onboarded to OPA. Now, let me call Sushanth to talk about a rate limiting journey.
Thanks, Sumit. All right, folks, let's have some fun. Let's talk about how things work, rate limiting and config distribution at scale. So these are the two things that we are going to talk about. Let's have a quick show of hands. How many of you know what is rate limiting? Almost everyone. Nice. So let's keep it simple. There's a service which says, hey, I am only going to take 3 requests per second. Right? So let's see what happens. Currently, all the users of this service access it using a new domain called service1.com. Let's see what happens to the request. The first request lands on the load balancer, hits a pod. The first pod, the pod allows the request. The second request, again, same thing. And yeah, the third request also landed on the third pod, and it was allowed. Now what happens to the fourth request? Yeah, this got rejected. So what really happened here? So we used the simplest rate limiting algorithm here. So we have 3 requests is the threshold, and we have 3 pods. And we said, hey, if every pod is going to allow only 1 request every 1 second, we are good. We have rate limiting, right? So this works when we have 1 service in the entire swim lane. So yeah, we were happy about this. Basic rate limiting works. What happened then? Sumit spoke about multi-tenant architecture, right? So we brought that into the mix. That means on the same swim lane, now we are going to host a bunch of services, and the requests are going to get distributed across all the pods. Now what happens to our rate limiting? What's the side effect of this? Let's see what happens. Let's say there are 2 requests for the same service, land on the load balancer. There's a good chance that they'll land up on the same pod. We just said load balancer is a round robin of requests, right? That still is true, but that is doing it across the 3 domains, service 1, service 2, service3.com, but not at a particular domain, service 1. Right? So now what happens? We allow the first request, and the second request, yeah, oops, right? So instead of 3, you get rate limited at the first request itself. The second request is rate limited. So this is, yeah, we're not really happy about this. Let's see what can be done. So what's the problem here? Essentially, we are not able to have a proper round-robin distribution across a single domain if you are a multi-tenant system. So if it was only 1 service, we could do this. But since we added 2 more services, yeah, things stopped working. So yeah, we can do one thing. Hey, you say, why do we want to keep the count on every pod? Let's use a cache and store the counter there. Let's see what happens in this case. First request comes up. Now the pod checks with the cache, hey, I'm going to increment the request by 1. Is it good enough? Is the total number of requests that is allowed less than or greater than threshold? Based on this, I'm going to allow the request to my service. So since it's the first request, we are good. What about the second request? We are still good. Third request, yes, the threshold is less, right? We're assuming everything's on the same pod here. What about the fourth request? Now we see in the cache that, hey, what about the total requests on across all the pods? Because all the 3 pods are updating the same key on the cache, and we are saying, yeah, the fourth request shouldn't be allowed. Simple, right? Now you may say, Sushanth, hey, what happens if the request lands on the third pod? It's still good. The cache is shared across all the 3 pods. So now all the pods are collectively allowing only 3 requests at any given point of time, provided you have a distributed, proper locking mechanism on the cache. So we are really good here, and yeah, rate limiting works. Yeah, what can go wrong? So we are updating the cache for every single request, so cache scalability is a problem. So what we noticed is with the cache that we were using, we were able to only do 1,000 writes per second, per key. So we had millions of keys. So if it was just 1 key that we were updating, we were good. We could update as many as we want. But since there are millions of keys, the cache system that we used had a problem that we couldn't do more than 1,000 writes at any given time per key. And what's the second problem? Obviously, there is latency, right? So every single request, we are adding a couple of milliseconds of latency going to the cache, which for a latency-sensitive system doesn't really work, right? So yeah, we're not really happy about this. Let's go to the next iteration. And also, you may say, hey, what, your service, you spoke about 1.5 million TPS. Now you're not able to have a solution for 1,000. So what if I want 2,000, 2,500, 3,000 TPS? What do I really do if I'm not able to write more than 1,000 times to a particular key? What are we going to, how are we able to scale this rate limiting solution? Yeah, let's see, what did we do? We used a fixed leaky bucket counter. Now let's see what's a fixed leaky bucket counter. So essentially, every pod gets a local bucket. That's an in-memory bucket. Let's see what do we do with this. The request comes in. We just update the local bucket. We did not update the cache. We did not increment the cache. And we allow the request to go through. Let's say the same thing happened for the second request. Now for the third request, we check with the cache, saying, hey, what is the total number of requests? What is the current count on the cache that is updated by all the different services, all the different pods on that particular key. We reconcile that value, and now based on this, the total count in the cache and my current bucket count, I'm going to take a decision that, hey, should I allow the request or not? So this was fine. In this case, it was less than the threshold. But yeah, finally, we are able to do rate limiting in this case. But yeah, something is missing, right? What now? Scalability, right? So if you really look at it, our traffic varies in the morning, in the off-peak hours. It's going to vary a lot. And we use Kubernetes, so we have a very dynamically scalable environment. And during peak traffic, it's going to scale out 500,000 pods and all those things. But during off-peak hours, it may shrink down to 10, 15. So what's the problem with all this? And also, you may say, hey, you have a multi-tenant system. There are multiple services. Not all of them have the same traffic requirements. Some of them may be small, some of them may be extremely big services. Now let's see what happens when we put all these things into a multi-tenant setup. Let's say somebody like to configure 1,504 as the threshold. Let's see, now this service gets 3,000 requests. So since the threshold is 1,504, you are expecting to block half the request. Simple, right? 3,000 minus 1,504, almost 1,500 requests have to be blocked. And let's say worst case, there are no requests on the other pods, no other services. Service 1, service 3 doesn't have any requests. What happens in this case? For the first, let's say we split this into two sets. Set 1, 1,500 requests. Set 2, another 1,500 requests. The first set of 1,500 requests, since we have 500 pods, gets properly round-robin distributed. Every single pod gets 3 requests. Right? And we just described our leaky bucket algorithm. So we allow, all the pods are going to allow 2 requests, and on the third request, we are going to update the cache. Right? So what just happened? So yeah, we allowed 1,500 requests, and since we are reconciling the cache value can be from 3 to 1,500. Let's say we got unlucky there as well. We got 1,500 as the value that's there in the cache. We reconciled it. Now the second set of 1,500 requests land in. Now what happens? All the pods, they're going to allow 2 more requests. Essentially, yeah, instead of 1,500, we allow 3,000 requests. Pretty sure we are going to have an incident, right? We send 2x the number of requests that are allowed that was requested by this particular service. The poor service now is saturated, and we have an incident. Yeah, we're not really happy about this as well. Now you may say, Sushanth, you said, what about smaller services? What if somebody has capacity of only 4 requests, right? I only have 4 request capacity. What do I do? Again, same, gets 3,000 requests with the leaky bucket algorithm that we spoke about. This thing is absolutely saturated. It gets 1,500 requests instead of 4. So yeah, not a good situation to be in. And also, what about extremely big services? 25,000 TPS is the threshold. The service is getting 50K requests. You are expected to block half of them. Yeah, we're saying 1,000. We said 1,000 TPS is my cache, right? We are not going to be able to support more than 3,000. Yeah, this doesn't work either. So our rate limiting doesn't really work, right? Yeah, so let's see what can we change to solve all this, right? So essentially, one size doesn't fit all for all these different types of services that we have. So let's see what can we do about this. So I said the bucket doesn't have to be a static bucket. So if you're getting 50,000 requests, we are expected to block 25,000. Instead of starting with the bucket size of 3, you pick a bigger number, right? You pick a bigger number, let's say 45. So now, 45, if the bucket size is 45, the first 22,500 requests are allowed. Right? That's when all the pods, they have cleaned up their buckets, and they have updated the values in the cache, and they all have the latest values that are available. And now for the remaining 2,500 requests, we shrink the bucket size. Right? From 45, we bring it down to 5. So what happens? Essentially, we can, if things go very well, we can rate limit at 25,000, but even if it doesn't, there can be, what we have noticed is we get an error of up to 10%, 5%, 10%. So that is what we have noticed with this implementation. So yeah, we're happy with this, but what about the smaller thresholds? You said, what happens to 4 requests? This is fine, right? Because if you have 4 requests, then I'm going to have a bucket count of 1. For every single request, I'm going to update the cache, and we are able to do 1,000 writes per cache. So this is just 4 writes that are going to happen. And after that, all the pods know that, hey, the quota is done. I'm not going to allow more requests into this. So smaller thresholds also work. So let's look at the learnings from our rate limiting journey, right? So one is services with smaller threshold, they cannot tolerate another 10, another 30, another 50 requests. So we said, hey, we'll give them extremely high precision. So we'll go update the cache for every single request. So that works for them. And services with a bit higher TPS, like maybe 10,000, they have a capacity of 10,000. Even if they get another 200, 300, it's not going to saturate it, right? It's OK. So if we are in a multi-tenant setup, we are able to serve both ends of the spectrum, the smaller services and as well as the bigger services. And also, if you say, hey, 1.5 million TPS is what we spoke about, so there could be bigger services as well, extremely big services beyond 50,000 TPS. Then what we do is we use the first algorithm that we spoke about, the per pod quota, and we hosted them in individual swim lanes. Right? So essentially, they have good blast radius as well, because 50,000 is sufficient capacity, sufficient TPS to have a swim lane of its own. So this is about our rate limiting. Let's talk about self-service. Right? So everybody loves self-service. Config distribution at scale across API gateway and service mesh. So since we are discussing rate limiting, let's take this idea forward. Same concept forward. Let's say we have one service in two beautiful regions, region 1 and region 2. And it's also getting traffic from API gateway. Right? So it's going to get north-south requests from API gateway and east-west traffic through service mesh. Right? So everybody's with me with this. Right? So north-south API gateway, east-west over service mesh. And let's say you want to configure rate limit. Again, you want to change the rate limit or set the rate limit at 50 requests per second for this particular service. Okay. So at 50 requests, 50 requests per second. So let's see what happens. So we'll see, hey, you have to configure it in two different places. We have north-south and east-west. So we know API gateway, it's a central place between, you have all the pods. It's a centralized configuration, can work here. So this is not a problem. But what about service mesh? Yeah, we have to, if it's rate limiting, you have to do it on the service cluster. So yeah, you do it here, and yeah, it's OK, right? So if you're using Istio, you configure an envoy filter or whatever is required to configure your rate limit in service mesh. This is really ideal, right? So now you have two different places to configure your API gateway and service. It's the same set of pods, finally, that's getting traffic from API gateway or service mesh. Do you really want to keep these two things? If you want to change a number, you have to keep updating both API gateway and service mesh and make sure they are not drifted out, right? So yeah, not a really good situation to be in. And also, with service mesh, you notice there are some configurations that go to a client side. Let's say you're talking about a feature like traffic dialing. So if you have to decide, if the client hosted in this beautiful client cluster 1 has to decide that I'm going to make a call either to region 1 or region 2, this decision have to happen on the client cluster. So the configuration resides in client cluster 1. So yeah, now the problem is there's some configuration that has to be done on the service cluster and another set of configurations on the client cluster, right? So now how do I educate thousands of my developers at Intuit, and hey, some configuration you have to do it at service cluster, some of them in the client cluster, and yeah, if you are extremely big service, extremely critical service, you may have clients across hundreds of clusters, right? That means if you want to change something, you have to work with hundreds of clients of yours. You're not really happy about this distributed way of computing, and yeah, you are thinking about all your decisions in life about adopting service mesh and all those things. You're not really happy about doing this. So what we want to improve developer velocity is we wanted to have unified config management. That means, hey, give me one place, one UI, one simple place where I can go make all my changes. And now this gets reconciled across both API gateway and service mesh. My developers at my company don't have to know about how a particular thing has to be configured, don't have to make any syntactical errors, right? If all of this can be abstracted, that would give us extremely good developer velocity, right? I want to change my rate limit from 50 to 75. Just give me one button, update one place. It gets updated to both API gateway and service mesh, That's what we want. Let's see how did we achieve this. So we have a beautiful developer portal at Intuit where most of the self-service configurations for all the platforms that we own are built into. This is essentially used by all the developers at Intuit for configuring any of their needs. So we have a beautiful traffic page. This is where all the configurations are updated. So if you want to change the rate limit again, this is the page where you go. Now this configuration gets stored in services registry. And we use messaging service. So why messaging service? We have to notify these two platforms, the service mesh and API gateway, that something changed. Right? It's an event. So yeah, we use an eventing service in this case, which is messaging service. Let's say what happens. So introduce the service mesh part of the world. Now we go to the same thing. We have two clusters where this configuration has to be updated about the rate limiting configuration. So how did we achieve this? Right? So we use this component called Navic. So this Navic provides this abstraction. It knows where is this service one hosted. It is hosted in cluster 1, cluster 2, or whether the configuration has to be done on your client clusters or on your service clusters. This is all provided by this Navic. And if you want to understand more in details of how this actually works, we presented this at KubeCon Paris, and this is uploaded in the CNCF YouTube channel. So yeah, but today's talk, we're going to talk about the second part of it, which we did not cover again last time. We're going to talk about the API gateway config distribution. So somebody made a config change, 50 to 75 TPS. This gets notified to gateway, and now the gateway has to get this value from some place, which is service registry. Sounds extremely easy, right? Why are we discussing all this? It's not so simple. Let's see what happens at scale. Right? So we introduced this, the box on the right side, which shows all the pods that are involved in gateway. And service registry and developer portal, I'm going to abstract it out and show it as service registry. Let's say, again, the user comes in, and yeah, we introduce a messaging service as well. The user comes in and makes a config change from 50 to 75 TPS. We use a messaging service. The messaging service notifies all the pods in the swim lane saying, hey, something changed. You have to go talk to the registry, which is where the config is available. Let me go read the configuration, and yeah, we're happy, right? So Sushant, it's extremely simple. What are you talking about? Scale, right? What happens if you have 200 pods instead of those 3 pods? What happens in this case? Now we notified 200 pods at the same time. 200 pods are going to make a call to my service registry pods. They're going to hit the database, and you now start having database issues. It's going to burn your database if all 200 come at the same time. You can say, hey, you can throw more resources at it. You can add more read replicas. All of that can be done, but we didn't want to do that. It's an engineering problem. We wanted to solve it without throwing resources at it. Let's see what can be done. Yeah, we are not happy about this whole situation. And the other problem that is also the second problem here is, what if the configuration that is inhaled, the configuration that is done, is actually something that you don't have a validation on in your service registries? It broke something on your API gateway. Then you have all 200 pods have consumed this configuration, and you have an incident. Yeah. So what can we do about this? We introduce canary release pattern, right? So what is canary release pattern? So you're saying, hey, instead of notifying all 200 pods, we are only going to notify one pod. So now this one pod of API gateway is going to make a call to service registry, read the configuration from database, we store it in a cache, and now if this the first pod that has inhaled this configuration is going to run a smoke test, it says, hey, this configuration looks good. Now if it thinks if the smoke test is successful, I'm going to use a messaging service to notify the remaining 199 pods that, hey, boss, this configuration is good. Now you can go get that configuration from service registry, and now the configs are not read from the cache. It's read from, it's not read from the database, it's read from the cache. So we have solved both the problems, right? So we have solved the bad configuration problem, as well as our database. We are not reading 200 calls at the time. We're saying, hey, this is fine, so things are working, right? Then what happened is, we have 30, 40, 30, 33 odd swim lanes. Some of the swim lanes are normal size, 300 pods, 400 pods, but some of them are extremely big. And for this big swim lanes, which have extremely big number of pods, 3,000 pods sometimes, if we make a config change, yeah, I have to keep my service registry scaled out. Right? So, and this doesn't happen so very frequently. So now just for those 1 or 2 events that may happen once a week or twice a week, we don't know when this happens. Yeah, we have to keep our service registry scaled out, right? So this is not an extremely good situation to be in. We have to pay for all this, right? We'll say, hey, let's move away from scaling out registry. Let's store it in S3, right? Hey, why not? So we use same thing. Canary release pattern, one pod gets notified. The one pod makes a call to service registry, reads the data from database. And now, instead of involving service registry, we just write it to S3. And if this configuration looks good, this pod is going to notify everybody that the configuration looks good. You are good to get the configuration from S3. And yeah, we save some money in doing this. Yeah. So let's quickly summarize whatever we spoke. So Sumit initially started us with API gateway, service mesh, ecosystem. How is all of this built on Kubernetes? We spoke about OPA integration, learnings from RESync integration. Rate limiting is in a multi-tenant setup with up to 10% error rate, and config distribution at scale across API gateway and service mesh. So if you really look at it, there are many different ways to solve all these problems. This is one of the ways. Yeah, we're here to share learnings about all this. So these are contact details, Sumit and me, Sushant. And we have a booth today and tomorrow as well, where we're going to talk about Argo and Numa. So if you want to learn more about all this, or if you have questions about traffic, whatever we spoke about as well, you can reach out in our booth. Scan this code if you want to follow us on about our open source work that we are doing. Thanks, everyone. You've been an extremely nice crowd, and hope you all enjoyed as much as I was enjoying this presenting. Yeah, thanks, everyone. And yeah, thanks to the organizers as well. Thank you.
Questions? Any questions?
Yeah, if you have any questions, yeah, we are around. Yeah.